Hey everyone, in this video I'm going to go through questions 13 through 18 of the USNCO 2025 local exam. So you can follow along with both the exam and the solutions document I've written in the description below. Question 13 is testing the ideal gas law, and it's asking for the molecular formula of a gas given some key values. So what we're going to lay out first is what we're given and what we need. We're given the volume, the pressure, and the temperature, and what we need is the molar mass, which we're going to find through the N value, the number of moles. So the ideal gas law is PV equals nRT, and we can rewrite this as N equals PV over RT. And from here we can plug in the values that were given: 722 mmHg as the pressure, 264 milliliters as the volume, and 22 degrees Celsius as the temperature. So I've done the computation here, converting mmHg to ATM, the milliliters to liters. We use the R value for LATM mole over mole K, and then the Celsius we add 273 to convert to Kelvin. And we get the N value of 0.0104 moles. And from here, since we know that the gas has 1.53 grams, we know the number of grams in a sample and the number of moles of that sample. So if you remember what molar mass looks like, it's just grams over moles. So we can calculate it with our two values here. And that gives us a molar mass of approximately 148 grams per mole. And what we're going to do from here is compute the molar mass of each of the answer choices. And we're going to select whichever one is closest to 148 grams per mole. Starting with A, we have that the molar mass is 24 plus 114, which is 138 grams per mole, so that's not our answer. For B, we have 36 plus 1 plus 95, which is 132, also not our answer. For C, we have 36 plus 1 plus 95 plus 16, which is 148, so that is our answer. However, I'll also calculate D here. That's going to be 36 plus 114 plus 16, which is 166 grams per mole. So C is going to be our answer. And if you're wondering how I calculated the molar masses of the gases in each of the answer choices, you should check out my solutions video to questions 1 through 6, because that explains it a bit more. Now question 14 is testing real and ideal gases as well as IMFs. So if you're more familiar with chemistry, you might know off the top of your head that 1 mole of ideal gas at STP conditions fills 22.4 liters, and that's what the question is asking. However, this comes from the ideal gas law, so I'm just going to show it real quick, and you'll see what the point of that is. So we have PV equals nRT, and we can rewrite it in terms of V as nRT over P, and plugging in 1 mole as the N, the R value, which is always constant, and then we have STP, which is 273 Kelvin and 1 ATM. If you compute this, we have 22.4 liters, and that's the exact value that's being asked in the question. So we're being asked which gas will have a volume closest to that. So if an ideal gas fills up 22.4 liters at STP, and we are at STP, essentially we're looking for the most ideal gas. And the most ideal gas is whichever gas has the lowest IMFs, because IMFs cause attraction between gas particles that make the behavior non-ideal. So we're looking for the weakest IMFs among the gases in the answer choices. So we're just going to go through those real quick. For H2, we only have London dispersion forces, there's no dipole moments. For carbon, the dipole moments cancel out because it's a linear molecule, so it's LDF only as well. For SF6, the same thing happens, the dipole moments cancel out. And for xenon, it's just London dispersion forces. So you might be wondering how to proceed with this problem if all of the answer choices only have London dispersion forces. However, remembering that the London dispersion forces, their strength increases with mass because of more electrons and more random fluctuations within the electrons, we're looking for the answer choice that has the gas with the lowest mass. And from here we can easily see that it's going to be hydrogen gas, You don't really need to calculate the molar masses of each of the answer choices because it should be pretty obvious, but you can if you'd like. Now, question 15 is testing ideal gas law as well as root mean square speed. So if you look at what it's asking which quantities are going to be greater for C2H2 versus CO for pressure and average molecular velocity. So some key things to note out here. We see that there's two identical steel cylinders, identical being the key word, same temperature, and equal masses. So for this problem, you really only need to understand what the actual equations are. So I'm just going to write them out here. We have the ideal gas law being PV equals nRT, and we can rewrite that as P equals nRT over V. And since we mentioned earlier that it's the same temperature and the same volume because they're identical canisters, T and V are going to be constant, and R is always constant, so we're only looking at this N here. And remember that it says equal masses of CO and C2H2. So since C2H2 has a lower molar mass, the number of moles is going to be higher with equal masses because you're able to get more moles out of the same amount of mass, if that makes sense. So since this N value is higher for C2H2 and it's in the numerator of the pressure equation, pressure is going to be higher for C2H2. So I is correct. Now for average molecular velocity, you've got to know the root mean square speed equation, which is V equals 3RT over M. Like I mentioned earlier, this R and T is going to be constant, so we're only looking at the M. And also, like I mentioned earlier, C2H2 has a lower molar mass. But since this time it's in the denominator, this is going to make the V bigger. So average molecular velocity is also going to be higher for the cylinder with C2H2. So II is correct as well. And since both are correct, our answer is going to be C. Now, question 16 is testing phase diagrams. So it gives us the critical point of carbon dioxide being 31 degrees Celsius and 72.8 atm. And it asks us to describe the composition of CO2 at these conditions. So I've laid out the phase diagram for CO2 here. However, you don't actually need to memorize this because CO2 is a fairly standard gas or a standard substance. And as long as you know what a phase diagram looks like and how it's generally laid out, you can answer this question fairly easily. So we see that the critical point is here, and the question was correct in its Celsius and ATM values. So we're asked for the composition at a lower temperature and a higher pressure. So from here, we're going to go left and up. So approximately somewhere here, which you can see is liquid only. And you have to know, like, generally what a phase diagram looks like and what it signifies to be able to answer that. So our answer is going to be B, liquid CO2 only. And if you want to see a more formal solution, you can see the solution, which is also in the solutions document. At lower pressures than the critical temperature, the substance is going to condense easier, so it's going to be turning into a liquid more favorably. And the same thing applies for higher pressures. Higher pressures favor higher density, and liquid CO2 is more dense than gaseous CO2. So liquid CO2 is going to be more favored, and overall, only liquid CO2 is going to be present. Now 17 is testing IMFs, and we can see that, of course, from the details in the question, the type of intermolecular forces. And we can also see that it's asking for the higher boiling point. And we know higher IMFs cause higher boiling points. So we're going to compare the IMFs of both ethane and fluoromethane to answer this question. So ethane is a fairly standard alkane. It's just 2 carbons surrounded by 6 hydrogens. And fluoromethane is essentially methane, except 1 hydrogen is replaced by fluorine. So looking at this, we see that ethane has no dipole moments, so no dipole forces, so only London dispersion forces. And for fluoromethane, there is actually a dipole moment here because fluorine is more electronegative than carbon. So we're going to see a shift in the balance of electrons. So this is going to have dipole forces because the dipole moments don't cancel out. So this is going to have both London dispersion forces and dipole forces. So you can immediately notice, given the fact that dipole forces are stronger than London dispersion forces, since fluoromethane has dipole forces and ethane does not, that's going to be the answer. However, you might notice that fluoromethane's mass is slightly higher than ethane's mass. However, this change isn't large enough to justify the significantly higher boiling point, and because of this particularly, dipole-dipole interactions are going to be the intermolecular force most responsible for that higher boiling point. So that's going to be our answer. Now 18 is testing packing structures. So this is something you have to know for USNCO, and it's consistently showed up on local tests. It gives us the structure of hexagonal closest packed, or HCP, and is asking the coordination number, or the number of nearest neighbors that the cadmium atom has in the HCP structure. So you can either memorize this or you can answer it by just knowing what these structures look like. So HCP is a structure with atoms in an AB-AB repeating structure where there are layers above and below a given layer with atoms in the gaps or hollows of a given layer. So if that didn't make any sense, essentially we can see, let's take this as a given layer. You'll notice that the layer above and below has the atoms in the gaps of the above and below layers. So you have to be able to either identify that or just memorize it. So let's take C here as our atom of choice to count the nearest neighbors. We see 1, 2, 3, 4, 5, 6 nearest neighbors in the layer that it's in, and then above it's going to have 3 more, and it's not drawn, but below there's going to be the same type of thing as there is above. So we're going to get our 10th, 11th, and 12th here. So our answer is going to be D. And if you do want to memorize this, just to answer this question significantly easier, here's the coordination number, which is the number of nearest neighbors of the packing structures. So simple cubic is going to be 6. Body-centered cubic is going to be 8. Face-centered cubic is going to be 12, and so is hexagonal closest packed. So you can, of course, just memorize that. That's personally what I did for the test because it makes this like a 5 to 10 second problem. So yeah, that's our answer.